Welcome back to 3.9 Lagrange multipliers. We have experienced all different types of maximization and minimization with the optimization that we did in this chapter with the 3.8 relative minimum, relative maximum, absolute minimum, absolute maximum. Today we are going to culminate all of that with a 3.9, the lesson 3.9, which is Lagrange multipliers. This lesson is a optimization on a boundary. So with a relative minimum, you would have with a relative minimum or a relative maximum, you would have an optimization in the whole domain. With a absolute maximum or absolute minimum, you would have a bounded optimization, where the bounded optimization may be on a boundary like this. So if you have a region R that you want to optimize it with, you'd optimize it right here. So this would be your region R in the xy plane, and it would map to all of the points up here. Now what we focus on, what we want, whatever this equation is right here, this will be on the test. Whatever this equation is on the boundary. So we're trying to optimize on the boundary rather than inside the boundary or outside the boundary or in the whole domain. So how does that work? We have this equation, which you guys should know what this means. You guys should know what this means, except that you guys don't know what this means. This is lambda. It's the multiplier in this case. So in order for a Lagrange multiplier to work, the gradient of f has to be equal to lambda times the gradient of g. And why is that? Why is that so? Why is that so? So, well, actually, first of all, what does this mean? This means that if I have a graph like f equals x squared minus y squared, that the level curves are gonna look something like, or no, not f equals x squared minus y squared. Let's go to this side, actually. So minimize distance to the origin of x, y equals 4. So what does that look like? Well, the distance to the origin is, you can actually write it as a function of f of x, y is equal to x squared plus y, or square root of x squared plus y squared. But we really don't want to use this square root of x squared plus y squared, because this is really, it's really hard to integrate, it's really annoying, and it's really hard to do Lagrange multipliers with. So what we'd actually be better off doing is defining a new function, capital F of xy is equal to f of xy all squared, which is equal to x squared plus y squared. So this is the square of the distance, and we know that x squared plus y squared is always positive, so this is legal. This is a legal move. So what does this mean when you go back to the analogy? So if we have the graph of xy equal to 4, it'll look something like this, right? Now, our x squared plus y squared is our graph or our function that we're trying to maximize. So this is the g function. Actually, I'm going to use a different color since it's the g function. This is the constraint. The constraint is xy is equal to 4. I literally cannot draw this graph. It's so annoying. Alright, there you go. This is xy equal 4. So where is this maximized? Or where is this minimized? Where's the function f minimized? Well, anyone with a brain bigger than a peanut will know that it's minimized at these 2 points. That is the distance closest to the origin. If you go further and further away from the origin, for example at this point, it will be farther and farther away. So it's minimized at those 2 points. Now if we take the function x squared plus y squared, and we actually draw level curves of it in the graph, what you're going to notice is these level curves are rotational. No, they're not rotational. They're circular. And specifically, these circles meet the constraint at this point exactly, and it is tangent. That's the most important thing, is it's tangent to the hyperbola. Why does it have to be tangent? For this equation to work, it has to be tangent. But why? Why does it have to be tangent? Well, if we take the tangent plane analogy, or if we take the directional derivative analogy, when you go across a level curve, your gradient or your directional derivative on a level curve, tangent to a level curve, your directional derivative is always 0. Why? Because you're moving across a level curve. Level curves means your value, your z value, your f value is going to stay the same. So if you're moving in a direction where your value is just going to stay the same, then you're not changing. So the derivative is 0. So the slope is not changing, the derivative is 0. Now if you go completely opposite to that, actually first of all let's do the directional derivative. If you remember the directional derivative formula, which is not that, you don't have a head, so du f of xy is equal to the gradient of f dot with the unit vector, which is equal to the gradient of f times the cosine of the angle between the gradient and the unit vector. So the cosine of the angle between the gradient and the unit vector had to have been 90 degrees, because cosine of 90 is 0. So cosine of pi, I'm going to say pi over 2 is equal to 0 when tangent, when u direction is tangent to level curve. So what if the direction is normal to the level curve? If the direction is normal to the level curve, then it won't be that anymore. If the direction is normal to the level curve, then we are moving in the direction either of fastest increase or fastest decrease. And if you want to minimize something, you have to move in the direction of fastest decrease. And if you want to maximize something, better move in the direction of fastest, or better be in the direction of fastest increase, right? So if we move tangent in this if we move tangent to the level curve in this area, because it's a level curve, basically what we're getting is like a relative minimum. See, the slope is 0 if you move tangent to the slope. If you move tangent either this way or this way, you get a slope of 0. That's what happens when there's a relative max. So it's the same thing over here, except we know that since the two level curves touch each other, kiss each other right at that very point, their tangents must be either parallel or anti-parallel. What's anti-parallel? Anti-parallel means one's going one way, the other's going exactly the opposite way. So that also means that they're normal curves. Or no, not normal curves. Normal lines. They're lines that are normal to the level curve, which is a gradient, also anti-parallel. So we could say that the gradient of f is like this, or a gradient of g is like this, and then the gradient of f is like this. We could say that. I don't know if that's actually true or not, but they are anti-parallel or they're parallel. And when vectors are anti-parallel or parallel, there's something called scalar multiples. So that means that one vector times a scalar or times a constant is equal to another vector. And it's because of that that we can use Lagrange multipliers. So how does this work in this example? So if we just go and we'll do our example right now, is f is x squared plus y squared. We want to minimize that. We just want to find the 2 points basically. And g is xy equals 4. So g of xy is xy. and that's equal to 4. So gradient of f equal to lambda times the gradient of g. So what does that mean? That means that 2x comma 2y is equal to lambda times y comma x. No, vector. They are vectors, y comma x. So what does that mean? That means 2x equal lambda y, 2y equal lambda x. We have 2 equations, but we have 3 unknowns. So where are we going to get our third equation? Right here. xy equal 4. So how are you going to work this out? We can work this out by doing, well, this is y is equal to 4 over x. And actually, yeah, that's your first example. That's your first step. So try to work this out by yourself if you can. If you can't, then I will start working out in 3, 2, 1. All right, y equals 4 over x. So we have 2x equals lambda, or 4 lambda over x. So 2x squared is 4 lambda. So x squared is 2 lambda. X squared is 2 lambda. Now what do we have? Or we could say lambda is equal to x squared over 2. That's probably a better idea. Lambda is equal to x squared over 2. So what else do we have? We have 4y is equal to, or 4, yeah, no, not 4y. 2y is equal to x squared, or x cubed over 2. So now what do we have? We have 4y is equal to x cubed, y is equal to x cubed over 4. So x times x cubed over 4 equal 4. So x to the 4th over 4 is equal to 4. X to the 4th is 16. So x is plus or minus 2. Now when x is 2, then what is y? Well, you get 2y is equal to 4, so y is equal to 2. And when x is negative 2, what is y? You get negative 2, y is equal to 4, y is equal to negative 2. And those are your answers. That's it. Now, do you have to evaluate what the lambda is? You need to know what lambda is. You don't. As you can clearly see, I did not find out what lambda was in this entire problem, except what lambda was in terms of x. That's allowed. But I did not find out what lambda was in this entire problem. And I was able to find that 2, 2, and negative 2, 2 are your critical points. So what comes next? Not that. What comes next? So first of all, we have to plug it in f, and then we have to take the square root of it because f is the square of the distance. So f will give you what? F at 2, 2, and negative 2, 2 will give you 8. And so f of 2, 2 will give you 2 square root 2, and that's your answer. All right, let's continue with the next question. Find the maximum and minimum of the function this given this. So let's do it. The gradient of f is negative 1 over x squared, negative 1 over y squared, and we have our constraint. And if we let g is equal to this function, if g is equal to this function, then the gradient of g is negative 2 over x cubed, comma, negative 2 over y cubed. So what does this mean? This means that negative 1 over x squared is equal to lambda times, or 2 lambda, negative 2 lambda over x cubed. And then negative 1 over y squared, this is the most disgusting handwriting I've ever had, is equal to negative 2 lambda over y cubed. And we have this as well. So what does this mean? What does this mean? We have this, so I'm actually just going to write that out. 1 over x squared plus 1 over y squared is 1. So how would we want to approach this? The way that I actually want to approach this question is first multiply everything by x, because I multiply this by x squared, multiply this by y squared. So this becomes what? This becomes -1 is equal to 2 lambda over x. So I could actually solve for lambda. Lambda is -x over 2. And similarly, this will give you lambda is equal to also -y over 2. Or it's probably a better idea to solve, okay. It's probably a better idea to solve for x, not lambda. So x is -2 lambda. That means y is -2 lambda. Why do I want to do that? Because I want to solve for lambda. I want to get lambda. So what's that going to be? I'm sorry, it's not negative, it's positive, because negative and negative cancels. I just wasn't reading the question at all. So 1 over 2 lambda squared plus 1 over 2 lambda squared is equal to 1. So that means 1 over 4 lambda squared. So 1 over 2 lambda squared total, because that's 4 and that's 4, and you get 2 over 4 lambda squared, which is 1 over 2 lambda squared. That's 1. So lambda is square root of 2 over 2, plus or minus square root of 2 over 2. So what if lambda is plus square root of 2 over 2? If lambda is plus 2 lambda is square root of 2 over 2, then x is square root 2, y is square root 2. If lambda, y, because if I plug it in this and this equation, I will get those values. If lambda is negative square root of 2 over 2, both x and y is negative square root 2, or negative square root 2. So that means that f of xy, or I wouldn't say f of xy, f of square root 2 is equal to what? Is equal to 1 square root 2 plus 1 over square root 2, which is 2 over square root 2, which is square root 2. And then negative square root 2, negative square root 2 is 1 over negative square root 2 minus 1 over square root 2, which is negative 2 over square root 2, which is negative square root 2. So that's your max, square root 2, on the interval, or not on the boundary, 1 over x squared plus 1 over y squared is equal to 1, and your minimum is negative square root 2. Let's do one more example. This looks scary. This looks terrible. I don't want to work this out, but I'm going to work this out just for the laughs. So, how are we supposed to work this out? In fact, I made this question impossible, so there you go. Now it's easier. ETXYZ. So we have the gradient of f is equal to, and you'll see why I made this easier in a second. YZ, ECXYZ, because it just copies itself, and then you take the derivative of the top, which is YZ, XZ, ECXYZ, XY, ECXYZ. Right? Nabla G, or gradient of G, is 2x, 4y, 8z. So let's do the multipliers. YZ, ECXYZ is equal to 2 lambda x. XZ, ECXYZ is equal to 4 lambda y. And then xy, ECXYZ is equal to 8 lambda z. So there's a neat trick that you can use to solve this question easily. And the trick is what I use. The trick is called substitution. So what I can do is I can substitute u is xyz etxyz. Why? Because this becomes a lot nicer. And what I can do is I can actually group them together. And you'll see what I mean by grouping them together in a moment. So u is equal to this. So this means that, well, u over x is equal to 2 lambda x. U over y is equal to 4 lambda y. And u over z is equal to 8 lambda z. So u is 2 lambda x squared, is also 4 lambda y squared, is also 8 lambda z squared. Which is very nice. This is very nice, especially in our constraint. So what you guys might say right now is divide by lambda, right? That's a pretty good idea, in fact. You should divide by lambda. But when you divide by lambda, you rule out the solution. You rule out the possible solution that lambda is equal to 0. So first of all, I'm going to say 2x squared plus 4y squared plus 8 equal to 8z squared. Or you can have lambda is equal to 0. So when lambda is equal to 0, what do you get? You get, from this equation, you will get either x is equal to 0, or y is equal to 0, or z is equal to 0. And when either of them is equal to 0, f is equal to 0. So when f is equal to 0, maybe that's the minimum, maybe that's the maximum. I don't know, but we'll see. So this can be simplified to x squared plus equal 2y squared equal 4z squared. So what now? Let's work it out. That's what. X squared plus x squared plus x squared. Because I can replace 2y squared with x squared because that's equal. I can replace 4z squared with x squared. That's equal. Is equal to 144. 144 is not a very nice number. I should have used 108 or something. So x squared, or 3x squared, is equal to this 144. So x squared is 48. So x is plus or minus square root of 48, which is plus or minus 2 root 12. Or, I'm sorry, 4 root 3. So usually I try x equals 4 root 3, and then I try y equals 4 root 3, but I don't really actually need to do that. Why? Because 4 root 3 and negative 4 root 3 is going to give me the same thing in this equation. So, especially x squared is equal to 48. So we have 96 is equal to 4y squared. Because 2 times 48. So y is equal to what? Y is equal to plus or minus 24, root 24, which is 2 root 6. And then we have the same thing. 96 is equal to 4z squared. Or, no. I'll just use this. So this is supposed to be, this is supposed to be 48 is equal to 2y squared, which still gives me the same answer. No, 48. And then 48 is equal to 4z squared. So z is what? Z is plus or minus 2 root 3. So all of these can actually be in combination with each other. Why? Because for any x or any y I put into the equation, I'm going to get the same y, or the same x squared and the same y squared, because squareds turn negatives into positives. So whatever x, y, or z coordinate I put in there, there's always 2 choices for the other and 2 more choices for the next one. So 2 times 2 times 2, that means 8 points. 8 possible points. I'm not going to try all of them because they're all just positives or negative versions of each other. Positive or negative. So what I'm actually going to do is I'm just going to go and multiply all of them. So what is the maximum then? It's not 0. The maximum is e to the xyz, which is e to the 4 root 3 times 2 root 6 times 2 root 3 And the minimum is the same thing, but negative. I'm so stupid. It's the same thing, but negative right here. So negative 4 root 3, 2 root 6, 2 root 3. Why? Because if we had a coordinate with 3 positives, that's the highest that you can hope for. You can also have a coordinate with 2 negatives and 1 positive, and it would evaluate to the same thing as well. It's not going to get any higher than that. The highest, the greatest z value, the greatest f value that you're going to get is 4 root 3 times 2 root 6 times 2 root 3. And simultaneously, the lowest one you're going to get is negative 4 root 3 times 2 root 6 times 2 root 3. Or negative whatever the lot is for the positive, because it's just a combination of the signs. And if there's an odd number of signs, then the value is negative. XYZ is negative. If there's a even number of signs, then XYZ is positive. It's just like that. All right. That's going to be it for today's episode. And we will move on to the next unit. I'm very excited for the next unit of multiple integrals. And we will move on to that in the next episode. And I will see you guys later.